Okay, Doc, I've conveyed the message to the other link.
All right. Thank you
Thank you.
so much.
Welcome, sir.
All right. Good morning once again. I think you can start from here while we wait for the others. So this is algorithm class, and it is coordinated by Dr. Regina A.C. Jackson. And for some reason, she's not here with us currently, but maybe as the class goes on, she might join earlier so that you can hear her voice. But then I'll be taking you through this course for the rest of the 4 weeks or more. And my name is Emmanuel Derry. And I believe we all are familiar or have heard of algorithms before. So I'd like someone to give us a brief overview, what you know about algorithm before I start. Anybody at all? All right, Clifford. Clifford, you're here again. What's up?
I'm fine, sir. How are you doing too?
I'm also doing very well. Thank God. Yeah,
Uh,
so what do you know about algorithms?
Algorithm is basically a step-by-step procedure in solving a particular problem.
Yeah, that is correct. Thank you so
Yeah.
much. Anybody else? Is anybody else? All right, Richard.
Yeah. To my point of view, I think algorithm is a step-by-step plan for solving a problem.
All right, thank you so much. Richard, the second Richard.
A step by step is a rule to be followed to solve a problem.
Okay,
A step
all
by step
right.
rule to be
Yeah,
followed.
thank you so much. So I think you all have a fair idea about what algorithms are. So we will not take much time today because this is more like an introductory lesson. And since you have a basic knowledge, I'll just walk you through what I have, and then hopefully next week we'll start with the supposedly the most difficult ones. And as Clifford and Richard said, algorithms are just step-by-step processes that we use to solve problems. And this, by the way, shows that in our daily lives, we basically or practically use this algorithm to solve a problem. And that is it. Today is Saturday, so you have your itinerary that you might go through to make sure the day ends and then you achieve your goals. And ideally, there's supposed to be a step by step. When I'm finished with washing, probably I'll go to the market and buy some food stuff and come and prepare food. All of these are processes that you go through to make sure your day becomes successful. And you could turn them as an algorithm. However, we are talking about computer or computing in algorithm here. So how does the computer actually follow the instructions that we give to it to give us the output that we desire? So that's basically what we are going to do for today. And this is basically the outline for today. So we'll talk about a brief introduction to algorithms. And then when we get to numerical algorithms, I might not spend much time there because this is more of basic stuff. And those of you who are teachers, you appreciate what I'm saying when we get there. And then interconnection networks and algorithms, shared memory machines, and the little complex one here is the string matching and data compression. But then when we get there, we cross the bridge. All right, so as you all said, algorithms are basically well-defined procedure that takes some inputs as values and processes the inputs and bring out what we call the output. But mind you, this is a computational process. As I said earlier, in our daily lives, we, one way or the other, employ algorithms. But then we are tailoring our discussion today to computing systems. So it is a computational procedure that takes some values as inputs and also produces some output as well. So this leads us to what we call inputs. And I believe all of us know inputs. And inputs are basically data to be transformed during the computational process of procedure. And then the output is a result that the algorithm gives to us, or what we expect the algorithm to produce or give us. So for instance, if you have to perform an arithmetic operation on 2 plus 2, in that sense, our 2 and then the double 2 becomes our input, and the result that we are expecting, which is 4, becomes the output. And this is to say that for every algorithm, it should be able to take input, and as well, it should be able to give us output. All right, so let's talk about some characteristics of algorithms. How do we differentiate an algorithm from any other thing that we have in the world? So one of them is finiteness. An algorithm should be finite. And then also it should be independent and definite as well. When we talk about definite, we mean that the steps, there are supposed to be steps that it will follow. Or what are the steps? What are the order of flow? How do we handle errors? So in defining an algorithm to be definite, we have to specify the steps that it will follow and what order should it follow and how do we handle errors in case that happens. So the example I gave earlier, 2 plus 2 to give us a 4. We all know that arithmetic operations only works on numerical values. What happens if a person provides a string like a name? So these are errors from the input. How do we handle all of them? So an algorithm should be able to handle all these errors, and then it should be effective. An algorithm should work more like every day. It shouldn't work today and the following day it stops working. That is, you program a calculator or you write an algorithm to give us the sum of two numbers. Today, 2 plus 2 is 4. Then the subsequent day is 2 plus 2 gives us 5. That is not an algorithm. An algorithm is supposed to be effective. And please, if you don't understand anything, just ask me and then I will go over again. And then also, an algorithm should be expressed in a clear and more concise way. This is very important because an algorithm is not programming language dependent. And it means that when it is clear and concise, anyone that is good at any of the programming languages can just pick it up and write it in it. So it's supposed to be very much clear and also it should be concise. And for us to be able to achieve this idea of algorithms being concise and clear, then there comes this pseudocode where we can achieve that clearness and concise in algorithms. And as you all know, pseudocodes are basically natural language to explain how a computational process should flow from the start to the very end that we have. So let's look at this example over here. We have this array of numbers and we are asked to find or search for 33 in the list below. Who can give us a brief overview of what we can do or how we can solve this problem? Yeah. Anybody? All right, Clifford.
So this one day I want to try you.
So don't worry, you can try for us. We are all trying.
So I want to maybe for all the numbers, we are looking for 33. So let's say if A is equal to 33, then print A, else continue.
Okay, all right, thank you so much. Please, anybody else? All right, Akutia, Richard.
Okay, sir. I believe to search for 33, we must go through them one after the other. That is 10. The 10 is not 33, so we move to the next one, which is 14, not 33, until we finally arrive at the 33, which is 1, 2, 3, 4, 5, 6, 7, which is on the position 7. So that's how I believe that it can be searched.
Okay, anybody else? Anybody else? All right, so I think what all of you said is true, but Clifford jumped to the middle and Akutia started from the beginning. That is fine. So let's combine both ideas and then try to see how we can solve this particular problem. And Clifford. Yes, Clifford.
Please continue, sir.
Oh, okay. Yeah, so as you can see on the screen, this is how the problem can be solved. And as Richard said, we have to look through the list. And then at each index, we compare the value that is available to the item that we are searching for. So we start from 10 over here. Then we compare 10 to the value that we are looking for, 33. Is 10 equal to 33? If that is not the case, we move on to the next 14. We do that until we get to 33, and then this value is equal to the item we are looking for, and then we exit. So this becomes our output, and these numbers becomes our input to the linear search algorithm, right? All right, so moving on, this is how the pseudocode will basically look like. And the first thing we'll do is we define a function, linear search, and the function is going to test a list. just as we saw earlier. And then also a value. That is a value we are looking up for. And then we look through the entire list. And then if there is a match to from the item that we have or the list that we have to the value that we are looking for, we return the item's location, then we end our loop. I mean, we end our if, and then we end the loop as well. Please, are we clear? All right. So basically, these are some of the things.
Let's go over.
No, please. So go over.
All right. So if you look at the animation here, we are looping through from 10 up to 44, right? And then what I was saying earlier is that we take hold of this particular one in every loop. And then if the value we are looking for, remember, is 33, we compare it to this particular first index value. If that is not it, we move on to 14. We compare 14 to 33. We do that until we get to the point where our item here is equal to the value we are looking for, 33. And then we exit. And then I was explaining the pseudocode over here for the previous animation that you saw. And then I said we declare a function which is called list array, linear search rather, sorry. And then we have this as a list. So the function will take a list and also it will take a value. And our list in the previous animation happens to be the numbers 10 to, I think, 14. Abudu, your hand is up.
Good morning, sir.
Good morning.
Please, the pseudocode, can you please explain the concept more?
You want to understand what pseudocode is?
Yes, please.
All right, so pseudocode is one of the ways to represent the flow of algorithms. You know, we cannot just get up and write the code in any programming language. Somebody might be good in Python, one other might be good in Java or C++ or C#. So it is best to write the code in a human readable language so that anybody that picks that document will be able to write it in any programming language that he or she is very competent or familiar with. So that is all about the concept of pseudocode. That is why you are seeing very much familiar words in here, like procedure, linear search, for each list, and the rest, right? However, this pseudocode is
Okay, sir. Okay, sir. Thank you, sir.
Relative to the outcome. This pseudocode is relative to what we just did earlier, searching for 33 in a list, right? And the pseudocode has a name which is called the linear search, which is a function that we are defining. And also this linear search, you have a list which we had earlier from 10 up to 44, right? And then also it should contain a value. That is the value that we are searching for from the list. So after this, we now have to look through, as Richard said, look through the list. And now we're trying to find the value that we are looking for. So this is how we look through the list. So for each item in the list. Now is the time for us to compare each of the items in the list to our value that we are looking for. So if any of the items matches the value that we have, we return the item's location, which is the item that is in the list location, to show that yes, this is the value that we are looking for. And then we end our if statement, we end the for, and then we end the whole algorithm over here. So basically, this is a pseudocode to search for a value in a list. Please, I hope it's clear. You right, Josh?
Sure.
You right, Josh, your hand is up, or is by mistake? And Clifford as well.
So I just want to make some clarification.
Okay.
What you have said, so it means maybe if there's a particular algorithm for solving a problem,
Yeah,
people can write the same algorithm or express the same algorithm in different programming languages depending on the platform they are using.
exactly.
Oh,
That is the
okay.
main idea behind pseudocode.
Okay, sir. Okay, sir.
Yeah. The righteous, your hand is still up. All right, so let's move. So these are probably some of the basic questions that might be asked. We'll give you a problem and then we ask you to write a simple pseudocode for it. And I hope you should be able to do that. All right, so let's move on and talk about correctness of an algorithm. And when we talk about an algorithm being correct, it's basically saying that for every given input, you should be able to hold and return the correct output. For every given input, it should be able to stop or halt and then also return the correct output that we are looking for. That is when we say that an algorithm is correct. But then let me ask, do you think every algorithm has the opportunity to halt? Does every algorithm halt? Ishan,
So please, mine is a question on the previous the pseudocode.
okay.
I noticed you use the double equal sign, and I want to know the meaning. Sorry to send it back a little.
Don't you know the meaning?
The double,
That is, yes, that is,
because
that
on the
is,
normal, I know the equal sign. If match item equals to value, but I noticed you use the double equal sign.
okay. So this is used to check for equality.
That's for the equal sign, the double equal sign.
Yes, that is check for equality.
You are assigning
No,
the
please, you're
value.
not assigning any value. You're checking for equality. Is the left side the same as the right side? That is what you're doing.
Okay.
Yeah, but if you use a single equal sign, then Richard could tell you, all right, you're assigning the value at the right to the item at the left.
Okay,
But
that
then
is
we are,
one is single.
yes, yes. But in this case, we are checking for equality in the value so that we see that we have actually found the value we are looking for.
Okay, sir. Okay, sir.
Yeah.
Thank you.
All right. Yeah, so I was asking a question. Is it possible for every algorithm to hold or stop? Uh, Precious, Precious, your hand is up.
Yeah, yes, sir. Please, I want to ask if the class is being recorded.
Yes, I believe code is recording the class. Are you asking to know that it's recording so that you can leave?
No, sir, so I can come in here and understand better.
All right, so code is recording. They'll give you the information when you ask them. Gideon,
Hello.
hello.
So I believe that for an algorithm to be deemed correct, they have to pause.
Yeah,
So in case it doesn't pause, it means it's not correct.
yeah.
That's my input.
Yeah, so I want to know, is it possible
Okay.
for an algorithm not to terminate or halt?
Yeah, it's possible when it's incorrect.
All right, thank you so much. So I would like you to go and find those algorithms that does not terminate or halt, right?
Okay.
Please, all of you are not only Gideon, but in actual sense, whenever we give input to any algorithm and it halts or terminates and gives us the correct output, then we consider the algorithm is correct. However, on the contrary, an incorrect algorithm may not hold on all or some given input instances. In some cases, the format of the input might not be suitable for the algorithm, so it will terminate without giving the correct input. In that instance, it doesn't mean the algorithm is not correct. It is just that the input format is not appropriate for that particular algorithm. Mind you, when we did the linear search, we said that the linear search pseudocode will take a list. So if you don't pass a list through it, and then you rather pass a linked list, or let me say different data structure to it, then you're going to get the wrong output. It doesn't mean that the algorithm itself is wrong, but then the input that you provided to it is making it incorrect. And in that same regard, we said earlier that the algorithm should be definite, that is, and should be able to handle error. So if the input is not appropriate, what do? You have to handle all those errors to make sure the algorithm is robust and correct. Is there any question? Is there any question?
Hello, sir.
Hello.
Please, sir. You asked us to do something, but I couldn't hear the instruction. Wait, please, can you repeat it for me?
All right. So I was saying that there are some algorithms that do not halt; they don't terminate. So we'll find some of them.
Okay, sir. Thank you.
All right. Dido, your hand is still up. Richard, David.
Yes,
Talk to
sir.
us.
So we were talking about the correctness of an algorithm, and I was trying to make a link with what we treated earlier. That's the characteristics of algorithms. Say for every even given input, it halts. That is if it is correct. But the part I didn't understand was the independence. If we say algorithm is independent, that side I didn't get it clearly.
Hello, David.
Hello.
Hello, Vicentia.
Yes. I can't hear anything again. Oh. Why is it his network?
Yeah, I'm also not hearing anything.
Yeah, I think
Hello,
so.
David.
Sir, please, sir.
Your hand is up, David.
Sorry,
So
sir. So we couldn't
right.
hear you. So if you can kindly go back again.
Yes, I mistakenly muted myself. So
Sir, I asked a question about the
Independent.
independence of an algorithm. Yes.
And from
yes, so I
that
was
time,
saying that,
yeah.
so I
Said
was
your
saying
question.
that For every algorithm, it shouldn't depend on the other to run. Just like what we saw earlier in the linear search. It doesn't depend on any other algorithm to run. So every algorithm should be independent of its own. So the linear search, for instance, is independent, except that you have to provide input for it to be able to run. Please, are we clear?
Yes, sir.
All right, so
Hello.
moving on. Hello.
Good morning, sir.
Good morning.
Yeah, please. In fact, the link is confusing as well. I perceive because there are other people who have joined the UCC, the link against the UCC and West School. And in fact, we waited, and there was no communication. So I don't know.
Maybe you joined very late. I asked one person here, I've forgotten his name, to join and ask everybody to leave and join here.
No, what he told us was those with the all other centers should join this line, this particular link. And those of us with the UCC and West School were still there waiting.
Please, are you still there now?
There are other people who are still there, and so I just came to verify.
Others are still waiting over there.
Yeah, so ask them to join this link, please.
All right.
Yeah. So even if you can share, I don't think you can share your screen, but ask them to join this link.
All right.
So please let's wait for like 2 minutes for all of them to join, then we can proceed.
Yes, I'm sorry, I didn't send the right information. I thought it was for all other centers for this class only.
Oh, no problem, no problem.
So.
Sir, I've disseminated the information to them, so most of them are coming here.
All right, thank you very much.
So then it means some of us are going to miss the beginning of the whole thing. Oh. I think I should put it right. We've already missed the beginning of the lecture. It seems where you are a little deep in it.
Yeah, so what should we do, David?
So please.
So, please, can you go back a little and just let's get the whole concepts, please. Thank you.
So I think for the sake of those who have just joined or those who are coming to join, we should start. Everything over.
All right, I'll try my best to do that.
Thank you, sir. Thank you, sir. Thank you very much.
This is more like the whole show. Richard, talk again.
Sir, kindly, you know, this course is a little bit
deep in computing, and therefore we have some who have not had any lessons in algorithm. So if you could do us this favor, it will really help us. Else we'll be here and then we'll be lost. It seems like we are following, but as a matter of fact, but if when you get a foundation, I believe we'll be able to build upon it. Thank you very much, sir.
All right. I think you can start now, hoping that everybody has joined. So as I said earlier, Dr. Regina, AC texting was supposed to be part of us, but I think in the course of the lecture, probably she'll join us and then you hear a voice. And this is algorithms. This is the outline, and some of your colleagues define an algorithm as a well-defined computational procedure that takes some values as input and produces some output. In that sense, means that every algorithm that we run, it should be able to take input, and if it takes inputs, then it should give you output. And when we talk about inputs, it is basically raw data that is to be transformed during the computational processes or procedures within the algorithm. And the output is the data resulting from every computational process or the result out of the algorithm that we have. So for the calculator that we use, there are algorithms written in them that give us the opportunity to provide inputs, and then they give us some output as well. So that's a basic overview of what an algorithm is. And we spoke about some characteristics or features of an algorithm. And these are some of them. We have the finite, the independent, it should be definite, and then it should be effective as well. However, you may add inputs and output as well, but then the output is not a solid point, but then the inputs are solid point in the sense that every algorithm should, one way or the other, fix an input. And we also said that algorithm should be expressed in the clearest and most concise way, so that anybody that picks it up can implement it in any other programming language. And for us to be able to achieve this clearness and concise in algorithm, we need to use what we call a pseudocode to be able to write them. And pseudocode are basically Abdul. And pseudocodes are basically patterns or natural human language that are used to explain the flow of the computational instructions that we write in the algorithm. And we give examples here, for instance, that we are given a list from 10 to 44. And the task is that we want to search for 33 in the list. How do we solve this problem? So Clifford said that we will we compare the values within the list, and then in each of them we compare to see if the value that we are looking for is in it, which is 33. And then Richard also said that you have to look through the list and taking note of their indexes at every point. We compare the value that we have in the list and then the item that we are searching for, 33. So we look through from 0, which is 0, which is the starting index. And then we compare the elements at the starting index, which is 10, to this 33. Is it equal? If that is not the case, you move on to 14. We compare 14 to 33. Is that the case? That is not the case. We move on until we get to 33, where this is equal to this. And then we see that we have found 33 in the given list here. So we demonstrated that using this animation here. We start from 10. We compare until we get to 33. And then we return from the linear search algorithm. And for pseudocode, for us to be able to get a concise and clearest understanding of how the linear search works, we provided this pseudocode over here. And then this pseudocode is a function which is linear search, and it takes the list that we saw earlier, which is 10 to 44, and also the value that we are searching for, which is 33. And then for each of the items in the list that we have, this is where we start looking through the items. If we have a match item which is equal to the value that we are looking for, we return the item's location, and then we end the if statement. And similarly, since we have found the item, we end the for statement, and then finally we end the whole pseudocode. So this is the pseudocode for the linear search you saw earlier. All right, and then we moved on and spoke about correctness of an algorithm. And we said that for every given input to an algorithm, it must halt and also return the correct information or output. Abudu.
Sir.
All right.
So it means if you are a developer and you understand this pseudocode,
yeah,
you can use it to, you can implement it in any programming language and any method. For instance, you can use for loop or if statement, right?
Yes. So that is the basic idea of the pseudocode for everybody who is good at any programming language to pick it up and then be able to implement that particular algorithm in that specific programming language.
Okay. So, yes, because now it seems I, based on my small knowledge, I can use if statement and also for loop to execute the pseudocode. That's why I'm asking to confirm.
Yes, that's true. So if you've been following the development of these programming languages, earlier on, when you write a program when you use a MacBook to write a program, you cannot run it on a Windows machine. So the best idea is that why wouldn't we write the procedures in a way that anybody can understand, and then when they get their own pieces, they can sit down and write it, rather than one person doing it on MacBook and the same code cannot be transferred to a different platform. So that is why the pseudocode is very much important. So for correctness of an algorithm, for every given input that we provide to the algorithm, it has to halt or terminate, and then also provide the correct output that we are looking for. It has to halt or terminate and provide the correct output that we are looking for. And when we talk about the definiteness as a characteristic of algorithm, we said that we should be able to handle errors. So it basically means that if the algorithm requires numerical values, you should be able to check and see that the input is solely numerical values, so that we don't even waste much time to execute the algorithm and then it will terminate without giving us the correct output. However, on the contrary, an incorrect algorithm may not code at all on some given input instances. That is to say that you give it the correct input, however, it won't halt and give you the correct output. Or it will halt all right, but then it won't give you the correct output. what we call the correctness of an algorithm. Please, I hope we are clear, those who just joined. And if you're not clear, code is recorded, so you might just ask for the recordings and go over again.
Thank you, sir.
All right.
This part is clear.
All right. So as I said earlier from the beginning, there's some part which is called numerical algorithm. And I said earlier that we all went to basic schools. We know the basic number system. So we wouldn't spend much time over here. So for integers, natural numbers, rational numbers, all of us are very familiar with them, right? However, if you're not familiar with natural numbers, integers, you can just alert me. I'll pick someone to help you understand it. And also devices and divisibility. I mean, we are all familiar with this. And we have another one we call a prime and composite number. So what is a prime number? Ladies.
Yes, sir, please. A prime number is a number which has only two factors. That is one in the number itself. Thank you.
Are you a math teacher?
I've taught maths for some time now.
Oh, okay. Then please take us through this one.
Is it the composite numbers?
Yeah, the composite numbers as well.
All right, the composite numbers are the numbers with more than two factors. So for instance, when we take 6 has the factors of 6 are 1, 2, 3, and 6. They are more than two factors. So those numbers with more than two factors are composite numbers. But the numbers with just the number itself and 1 as their factors are the prime numbers. Thank you, sir.
Thank you so much. You deserve an award. Please, who don't understand what she just said? She has actually summarized the whole slide for us. So all these mathematics that you are seeing are basically what she just said. Right. Can we move on, or anybody that has a question on this? All right, so let's move on to what we have here as some algorithm for interconnected networks. But please, what is a network in the first place? Have you done networking?
No.
Haven't done networking yet.
No,
Jackson.
sir.
Jackson.
Okay, so thank you. Well, when we talk about networking, you're talking about a process whereby two or more computers are connected so that they will be able to share resources. Thank you.
All right, thank you so much, Jackson. Clifford.
So I think it's the same thing. The connection between two or more computers for the purpose of sharing information and resources.
All right, thank you so much. So ideally, what these algorithms for interconnected networks does is that they, as you said earlier, they share resources. And if there's so much devices that are connected to the network, there exist multiple paths that we can pass through to reach a destination. And in this case, these algorithms, one way or the other, select one path and then referring to the other paths as well. So that is what these algorithms basically do. So if you have, let me say, 16 computers that are connected together in a network, it obviously means that if you start from computer 1, you have several paths to move on to the destination. And these algorithms select one of the paths by referring to the other paths as well. And then this process can be called routing, where the information moves from the source through the other nodes in the network or the devices in the network to the destination. In that process, they select the path by referencing or preferring to the other paths as well. So let's assume, for instance, this is our computer and this is our server. All of these are other devices that are connected to this particular whole network over here. So in essence, we can say that we want to route our packets or our resources or our information from this laptop to the server, or we want to transfer our information from this laptop to this particular server. And you realize that we have so many paths that we can pass through to get to the server. So one of the packets might pass through here to this place here, and then finally get to this place. Or one of the routes could also be from here, go to this direction, and then this one. Or another route could be from here, more like this. So all of these ones, in the process of sending the information through the various nodes to the destination, are called the routing. And the purpose of these routing algorithms is to select one of the paths and then send the information to wherever destination that we are sending it to. So let's look at some of the routing algorithm or the algorithm for interconnected networks. So one of the things is that these routing algorithms fill routing tables with a variety of information, such as the address, source address, destination address, and distance from various nodes, and many others. So in the process of routing, these are some of the things that are stored in the let me say data structure, which is called the routing table. We have the source address, the destination address, and then the distance from various nodes. So the source address basically talks about where the information is from. The destination talks about where you are sending the information to. So keeping these ones, make sure that the packet or the information that we are more or less sharing on the network doesn't get lost. So if it doesn't get to the destination, obviously it has to come back to the source. So we have some types of routing algorithms. We have the static or non-adaptive routing algorithm. In this process, the routing course or the path is fixed, irrespective of the network conditions. So the path for this particular routing algorithm is fixed, irrespective of the network conditions. So assuming we have this, we have several paths in this particular network here. But if we are going by the static or non-adaptive, it means that the path from this, where we route information to this server, is fixed, regardless of any constraints that we set on the various paths. So we can choose this particular path in a sense that whenever information is being transferred from the computer at the left to the server, it has to pass through this route, regardless of any constraint that we have set on this. And it doesn't matter if it is the shortest distance or the shortest path, or it's not the shortest path. The idea is that the routing path should be fixed for every packet or information that is being transferred from the source to the destination. That is what the static does. And then the dynamic is the opposite of the static, where the course or the path will change as per the conditions of traffic. And I think we quite experience this in real life situations. Those of us who, one way or the other, have been to towns where there's heavy traffic. So instead of the drivers following the traffic, you see them go through different routes and then come back to the main road, and then they set off to wherever destination they are going. So this is a clear example So if you send a package from, let's say, this server, this device to the server, and then it gets to this place and realize that moving on to this one, there's enough traffic over there, then it will have to now switch to a different path and then make sure you get to the destination. So the path is not actually fixed as compared to the non-adaptive routing algorithm. Please, are we clear? All right.
Sure.
You righteous? All right, so we have what we call a dimension ordered routing, where we have deterministic algorithms which has predefined path from the source to the destination. So this one has a predefined path from the source to the destination. And in the DOR algorithm, at the source node, the node pre-compute a set of preferred destination to route the packet within. The nodes pre-compute a set of predefined directions to route the packet within. So this pre-computing might be cost on the edges of the network path. That is from, let's say node A to B. What is the cost as compared to node A to C? If node A to C is less or shorter, then it will compute the route and choose that particular short one. So that is what is going to be done. So for instance, if you take this particular path here, for instance, this is the starting point. So it pre-compute that it will go through 1, 2, and then 5 instead of going to 3. Because realize that when it goes to 3, it's going to make the journey very long. So it will take a dive from 2 to 4, then 4 to 10, 10 to 14, 14 to 13, 12, and then to the destination. So this is how the DOR really works. It pre-computes a set of predefined destination to route the packet within. But it is not always the case that it chooses the shortest path. Maybe for some reasons, it recalculates and choose a different path. So if we look at this particular place here, going from 10 to 11 will get you to the destination very quickly, but then it decided to pre-compute and move to 14. Probably during the packet transmission or the information transmission, where it got here, the traffic from 10 to 9 was very much high. So it has to pre-compute or recompute the directions and then move to 14 before it gets to 13, then the source destination, the destination. Please, are we clear?
Yes, sir. Like the same way, moving from 0 to 4 would have been the shortest route, but I chose to the other way around.
0 to 4, yes, mind you. Okay, that is if 0 to 4 is connected, yes, that would be the best option to go. But then probably the way network, I mean, there was a lot of traffic here, so we decided to move to 1 and then before to route to the source, I mean the destination. So that is the deterministic, I mean the DOR, dimensional ordered routing. And I also have the directional ordered routing, which is a variation of the dimensional ordered routing that introduces the concept of direction within each dimension. So this is more like an extension of the one we just learned earlier. However, this one introduces directions. Yes. So you realize that for all this routing, there's no direction showing which flow the network should go. So it means that the algorithm can pre-compute using any of the nodes. But then as soon as we add directions to it, it means that the directions are going to follow the flow of the route that we have. So assuming that we had a direction from, let's say, 1 to 2, which points in this direction? Let me say the opposite direction. It means that if we are doing the pre-computing, we cannot use the 1 and 2 because it is against our movement. I don't know if you get what I'm saying. Do you get what I'm saying?
Please take it again.
No, sir.
Yeah, so what I'm saying is that.
Okay.
Hello.
Okay. What I'm getting to understand is with the dimensional ordered routing, that one too determines direction. But based on proximity or hello, sir.
Hello. Yeah, you were saying
Yeah,
something.
what I'm
I didn't
getting
hear
to
you.
understand is that with the dimensional ordered routing, it also determines direction, the direction of flow.
Okay.
But based on proximity.
Okay.
That is what the idea I'm coming out with from what you are presenting. And I want to know if it
let's do we understand what is happening here? For the dimension ordered routing.
Hello.
Gideon.
Yeah, boss, please, can you please go back on the routing, like a quick wrap up on the routing again for us? I'm getting confused.
You mean this slide?
No, only on the routing, no. Like introduction on the routing.
Okay, so you mean this?
Yes, please.
All right, so what I'm saying is that some of your colleagues said the network involves a connection of several devices and most preferably to share resources. So this is an example of a network setup where we have this computer over here and we have other devices over here. So these devices can probably be routers, they could be switches, they could be other devices like the computers and laptops as well. And this is the server that we have, right? So in a way, if we try to share the resources from our computer to the server, we definitely need to choose a route. Where should the resources pass through before it get to the server? So in that process, that's what we call routing. We are routing the information from the source, which is our computer, through the other devices that are on the network to our server. So that is what we call routing. So we could choose this particular path here and then route our information to the server. Or we could choose any of this path from our computer to the server. I hope it's clear. Usman.
Please, will there be an instant where it will choose multiple paths and arrive at the same destination?
Yeah, it's very possible. So if you realize in some cases when someone sends you a picture and you try to download it, the paths will start becoming clearer as it times goes on. So it means that some of the packets have not arrived, and so therefore the image is not clear. But as soon as all the packets arrives, the image becomes clear. So when the packets or the information are sent out, some of them can use a different route, which may cause them to arrive to your device very late. Others might choose a very shorter path and get there very early. So when those packets that get there early, you start downloading the image and then you see that it is blurred from the start. And as time goes on and all the packet begins to arrive, the image becomes clear. So yes, some of the packet or the information can choose different route, but then since they have the source and destination addresses, they will never get missing. Are we clear? All right, so
Sir,
Salon.
please, some of us are, in fact, we are novice also. Don't be worried about choosing the path.
Yeah.
How do I choose? Practically, how do I choose a path? I really don't get it
Practically.
because.
Yes, so choosing a path is also writing an algorithm for you. So I think you probably get there, but then let me give you this overview. When you write the code, especially this static what we have here, this static and non-adaptive, you can write a code to make sure that any packet that you send goes through a fixed path. They don't have to spread and take different route before they get to their destination. So you, the programmer, will have to one way or the other write those routing path for the algorithm to follow. But then ideally, the various devices that we have, the switches, the hubs, and even some of the computers that we have, they have already built those routing algorithm for us. So we don't need to do much. All we need to do is just send information and then you sit down and see how they can be sent to us. Right? But then you have to get to understand that in some instances, to our computer system, we could have a static or non-adaptive routing algorithms that will route the information we send from our device to a different machine. The same way we can have dynamic as well, which means that they'll take different paths regardless of the, per the conditions of traffic on the road, or let me say on the various paths that we have or the routing paths. Please, are we clear? So you, the user of the system, you're not supposed to be bothered about the routing algorithms. All of these are built into the operating systems and the other servers that we have. But you should know they exist. Please, are clear?
Yes, sir.
All right. So in the computer system, like our various machines that we use, the devices, the mobile phones, and the rest, they have built a static or non-adaptive routing algorithms, which uses a fixed course irrespective of network conditions. And we have also the dynamic or adaptive path. For this routing, the course of the path will change as per the conditions of the traffic. So as one person asks, is it possible for the information we share to take different paths? Yes. And this is a clear case over here. So if it's a dynamic or adaptive routing algorithm, it basically means that if the packet is moving and realize that this is network here or there's traffic over here, sorry, then some of the packets will move to a different path to make sure they get to the destination. Richard.
Yes, sir. So with the definition of routing, can we say it is a process of choosing a path to send data from one device to another in a network?
The definition of?
With the definition of routing, can we say it is the process of choosing a path to send data from one device to another in a network?
Yeah, you can say that.
Okay, thank you.
Please, any other question? All right, Osman.
Yes, sir. The packet we're talking about the same packet. What if it is a different packet, but they are all computing on multiple paths to get to a one destination?
I don't get the question. Can you come again, please?
Listen, I'm saying that when you were talking about the path, you say only one packet could move through different paths to get to one destination. So I'm
Yeah.
asking what if it is a different
Packets.
Sorry, this is a different packet and they are all moving on a different path to get to one destination. How will that one also be?
Yeah, if I get the question right, you want to say that, let me use a document for example. You want to say that you are sending, you want to say that you are sending a PowerPoint file, and also you are sending a Word document, right? Is that correct? Because
Yes,
these are
please.
going, all right. So each of them, when you send a PowerPoint file, the file has a source and destination. So regardless whether they mess up with the document file or not, they are still going to get to their destination, even if they use different paths. I don't know if you get what I'm saying. All right, please, any other concern or question? So please, those of you who are novice, when we say packets in networking, any information that is passing through the network is called packets. So the packets can be network signals, it can be your Word document that you are sending, your pictures, your videos, all of them can be packets. So please just don't get confused about what packets are.
Sir, please, can you come over again? The packets.
Yeah, so what I'm saying is that when we say packets are basically the file that we are sending over the network. But ideally, in networking terms, we call them packets. So if you send a picture, if you send a video, if you send an audio, all of them passing through the network are mostly referred to as packets. Right?
Okay, sir.
Abunu.
Sir,
Okay.
please, is packet different from frames?
Is packet different from
a frame in networking?
A frame.
Yes.
What is a frame? Because frame can also be found in HTML. So please, what do you mean by frame? Can you explain?
Yes. Here we're learning networking at College of Education. They mentioned packets and frames interchangeable. So I thought they were the same.
I'm not saying they are not the same. So what is a frame in your context? Because I said we have frames also in HTML. So if you can explain the frame that you're talking about, I can give you an answer.
Okay. Based on my understanding, then it seems what you are saying is the same as what they told us at college. That's why I'm asking if there's a little bit of differences.
Well,
so
so yes.
I want to read something about frame here so that we compare.
Okay.
From here, they say a frame in networking is a unit of data at the data link layer that packages information for transmission over a network, including the sender's address, receiver's address, and error checking details.
Yeah, so that is it. So they can be used interchangeably, as you said, if that's the definition he just gave. Is it clear, Abudu?
Yes, sir. Thank you, sir.
All right, please can we move on now?
Okay, sir. So
Yes, please.
please, I want some clarification here.
Okay.
Sir, since they are used interchangeably, does it mean that they are the same? is packet the same as frame, or they are not the same, but they can be used interchangeably?
Yeah, so it's more like saying a child and I think a toddler. How don't we use them interchangeably? But then they are not the same. So they somehow have some similarities. That is why we mostly refer to them as the same. But if you look at the definition that was said, he said that it's the smallest unit of the package. I don't know if you get it. So yes, we could say in a very broad sense that they are the same, but there could be some small disparity between them. Ishan.
So let me talk a little about the packet. I mean, my own small understanding. Maybe it can give a little. So with the packet, what I understand is that it's a data, be it video, picture, but when they are being sent through a networking system, it is broken into pieces.
Okay.
It is broken into pieces. So once you are downloading, as you said, the data doesn't come in bulk. It is broken into pieces, which are known as packets.
Yeah.
And once it reaches the destination, they all join together to form that video, that how they call it, picture and stuff like that. So it's just data, be it video, picture, anything that we download. But once it's passing through a network channel, it has to be broken into pieces, which is called packet. And then once it gets to the destination, they all join together to form one unit of data from at that destination ending. Bro, if you can get, maybe it's the smallest unit that they term as a frame, but what I know generally is that packets are the data that are being transmitted, but has to be broken into pieces so that, and then while it's broken into pieces, they go through different parts, but then they will arrive at the destination, they join together to form that video, that picture that you downloaded or that you sent. Bro, if you can, I don't know if it makes some sense.
So when does the frame? You didn't mention the frame. It seems you are targeting only the.
All right. So let me
maybe the frame is, you said the basic unit. If I understand the definition that your colleague, the guy gave, the basic unit for the packet is how the data is broken into pieces and channeled through the path to get to the destination. So maybe the units, the smallest of it is what we call maybe the frame. I'm just, but what I know is, as I said, the packets are how data are broken into pieces while they are being routing. And once it gets to the destination, they all join together to give you that video, to give you that picture that you downloaded or you are retrieving.
Thank you so much. So let me just bring up the disparity between them. So when we talk about the operating system, right? We have so many layers in the operating system, especially when it comes to data transfer. We have the network layer, then we have the data link layer, right? So if the information we are sending are found in the data link layer, then they can be called a frame. If they are found in a network, then they are called packets. And in the packets, that is where we add the addresses like the IP addresses. That is the network layer. So if we have a packet, it means it has an IP address. However, if it is a frame, then it has the MAC address of the source computer. I don't know if you get what I'm saying.
Sir, for my part.
For your part. Please, is it okay? Please, any question? So packets are transferred through the network segment. However, the frames are mostly on the data link layer. And the difference is that one of them has the IP address and the other has the MAC address. And the IP address are mostly configured over the network. And the MAC address are mostly resident on the source device. These are we clear? So in as much as we can use them interchangeably, but then these are the small differences that we can actually have from them. I think Richard wanted to add something. Richard.
So what I wanted to read, you have said it. You have said it already.
Oh, okay. As I think you can proceed to where we are finding difficulties in understanding. David.
So in sum, we can now say that frame and packets can be used interchangeably because they all refer to a unit of data being transmitted.
Yes, but then if they want you to differentiate between them, then what I just said is what you're supposed to tell them.
All right.
Yes.
Thank you.
Okay. All right, so let's talk about the dimension ordered routing list. And as I said earlier, this is a deterministic algorithm which has a predetermined path from the source to the destination. And then in the DOR algorithm, at the source node, the node pre-computes a set of predefined directions to route the packet within. It computes preferred directions where the packet can be routed within. And as I explained earlier, from 0, you move to node 1, then 2, then 4, 10, 14, 13, 12, and then 8. So this is the pre-computed set of preferred directions where the packet should move from the source to the destination. Please, are we clear? And there is no back and forth in this particular process. There's no back and forth. That is, if you move to the next node, you can't really go back to the previous. Please, are we clear?
Yes, sir.
Yes, please.
Usman.
Please, does it always have to be because of traffic that it always diverts its path?
Yeah, so not necessarily only traffic, but then if one of the paths is broken, obviously you need to choose a different one. So it doesn't mean that all on one path there should be a lot of traffic and then it will divert. If the path is broken, especially if we got from, let's say, from 1 to 2 and then 2 to 4, and realize that 2 to 6, the path is broken. Maybe the network cable is broken. Let's assume you're using a LAN cable and the network cable is broken. Obviously, you cannot move from 2 to 6 anymore. It has to move to 2 to 3, and then 3 to 4 before it continues. But in most cases, it is network traffic. John Aiden.
All right, sir. Please, I want to find out what if there is a heavy traffic on all the paths. What will be the situation?
That's why in most cases your information takes longer to load. Right. That is why in most cases the information takes longer to load. So if all the paths are only 3 and all of them there's huge traffic on it, then obviously they will have to join the traffic. when all other packets are delivered and the road is free, then the path is free, then they will all flow through to the source, to the destination. Right. And as I said earlier, with this particular one, there's no back and forth. You don't have to move from 0 to 1, 1 to 2, and then 2 to 1 again. That is not really allowed in the dimensional ordered routing. However, in the
Sir, please, you said that with the laptops, or our computers, you said they have already created a path for us to, use. Of which, when you are sending information, you have already created a path of which to follow, and then the information is passed on from this one to the another one. And I want to inquire. So, does it mean that those laptops, those computers that came previously, they created a longer path for them in order to send an information? That's why they run slow, or what?
All right, so let me clarify this. These are algorithms that are built within the operating system. The routing paths, they are all within the operating system. So yes, when as technology evolves, then they develop more ways to make sure that the transmission is much more faster. I don't know if you get. So it means that previously, the technology that were used to design these routing algorithms were not quite efficient. So they couldn't really route our information quite quickly to their destinations. However, these advanced machines, they have built in quite efficient and effective routing algorithm to make sure that information is routed quite quickly and faster. All right, John Aiden.
Sir, sorry for bothering with questions.
Yeah.
My another one is that when we were, I think in the previous block, when we were learning about operating system, we talked about a kernel. And I want to find out that we said the kernel is the core when it comes to operating system. So we want to know actually where actually does this one takes place. Is it from the kernel itself, or it takes place or within the operating itself? Actually, that's what I want to find out. Thank you.
Please, can you ask the question again? Sorry for that. Okay.
What I'm saying is that when we were, during our previous book, we were talking that the kernel resides within, the kernel happens to be the core of the operating system. Now, with the algorithm that we are talking about here, we are talking about path and we are saying it also deals with the operating system. So we want to know whether is it the operating system in general, or it deals with the kernel or whatever. I don't actually. Can you help us with that one? I know I'm taking you back or something, but you will help us with this one.
So it is the OS in general. All the various components that we spoke about in what's the name? Operating systems works together to make sure that every algorithm that is built within the operating system works. So yes, if there's a need for a kernel to invoke any routing algorithm, it will do it and then send the packet out. If there is no need, then it won't. Is it clear?
All right, thank you, sir.
All right. So this is how the dimensional ordered routing looks like. So it moves into one direction, and then before David.
Sir, as our brother asked that question, it prompts me to inquire, or let's say add. I want to say that I know there is data transmission even within the same computer. For example, you're able to connect storage devices to the computer, whereby you transmit data from the computer onto that storage device. So this means that when you are transmitting that data, there is a routing that takes place for the data to be transmitted or to be sent from that computer to the storage device you have connected. Or let's say you're retrieving an information from a device, or let's say you are connecting a printer to a computer, meaning there's a routing that takes place. So it's not only like excuse me, it's not only like in a network system alone, but within the computer and using the peripherals too, there's also a routing that takes place. And therefore the kernel or the operating system can actually evoke routing to take place whenever the need arises. That's what I want to add.
That is very true. All right, so let's move and talk about the dimension ordered routing. And as I said earlier, there's no back and forth in this particular routing order, right? There's no back and forth. So it basically means that you have to route in one direction. When you are done, then you can also move to the other direction as well. All right, however, when we go to the directional ordered routing, it's the variation of the one we spoke about earlier, but introduces the concept of directions within each dimensions that we have. So instead of fully routing within the X direction before progressing to Y, and so on, the directional ordered routing route positively within all directions first, then route negatively within the directions last. That is to say that the directions are taking a fixed order, and once you move forward, you never reverse again. Please, I hope it's clear. So once you move forward, you can't reverse again. So we have zero. So look at this particular one here, for instance. This is more like let me say a matrix. So 0, 1, then move to 1, 1, then 2, 1 in that particular order, right? And then also we move from 0, 1, and then go to 1, 0, then 2, 0. The directions are taking a fixed order, and once you move forward, you never reverse again. So you take a step forward, you cannot come back, probably to recalculate or reorder your steps again. As soon as you move one step forward, you're not going to come back again. Please, are we clear? All right. So now let's talk about shared memory machines algorithms. And I think this one, some of us are quite familiar with them. So in this shared memory machines algorithms, the main goal is to increase performance and resource sharing among various components of the computer system. And these are some of the algorithms that we have. We have the client-server algorithms, the migration algorithms, and we have the read replica algorithm. And when we talk about client, please, who understand what a client is? What is a client, or what is a server? Usman.
Let's say the difference between the server and the client is that the server provides the information and the client takes the information from the server.
The server provides the information and the client
takes the information from the yes, please.
Also, in this instance, when we talk about client-server algorithms, we mostly see that the data that is shared between these people is purposely maintained by the central server. So the server that is providing the information for the client, all the data that flows between the client and the server are being maintained by the server. And then other nodes of the distributed system request for reading and writing data to the server, which serves the request and updates or process access to the data with acknowledgement of messages. So all the nodes, and the nodes can be our mobile devices, our tablets, our laptops. So all of these nodes are connected together, and then we mostly call them distributed systems. And then they will make requests for reading and writing the data. And this request goes to the server releases the information, they read and write, and then they update the information. And in the process of updating the information, they acknowledge with messages. Maybe it is successful. You've been able to update the message successfully, or you are not able to delete some information as well. So that is what the client server algorithm really does. All the shared data within the distributed system are managed or maintained by the central server. And the nodes, which are maybe our mobile devices, tablet and laptop, request from the server to read and write data to it. Please, are we clear? Questions?
So please, is the client server algorithm the same as the central server algorithm?
Central server algorithm. What does that one do?
With that one, you see that it maintains all the shared data. It responds to input requests from connected nodes and updates data from writing requests.
Obviously, then that is it. So it's the same. It's the same. So either client server algorithm or central server algorithm, it's the same thing, provided they do what we just explained here. Please, any other question? And also we have the migration algorithm. So what the migration algorithm does is that it works on the migration of data elements. So instead of using a central server which serve each request, the block containing the data requested by a system is migrated to it for further access and processing. So for instance, if I request some information, the block containing the data that I requested is being sent to me, and then I don't have to do whatever processing I want to do to it. Is that we clear? So basically, that's the work of migration of the data element from the server to the finally requesting for the information. And then we are saying that what might go wrong here? Anybody to help us? What might go wrong here? All right, so just go and ask GPT what might go wrong if we try to use the migration algorithm. And then when we meet next week, I'll ask you. Then also we have the read replica algorithm. Robert Menza.
I want to suggest something. Since as compared to the client server algorithm,
okay,
this one, the migration one, I think there could be some kind of delay in terms of transmitting the data.
Yeah,
because
that's
it has to migrate, go through a long route,
yeah.
and then other processes.
Right. Thank you so much, Mr. Robert. That is very true because the block is a whole block, so it's obviously going to be very huge. You know, transmitting a very huge data over the network to the client is going to take a long time.
Okay.
And when the client finishes, the same way you have to now send it back. And that's a lot of data to be transferred over the network. That will make it quite slow. So that is very true. All right, and then in the read replica algorithm, the data block that is to be accessed is replicated, and only reading is allowed in all the copies. So the data block is replicated, and we can only read the data that's being given to us. However, if a write operation is to be done, then all read access is put on hold. So all the copies are updated. So let's say you've shared a Google Docs, for instance, to a client, and now you try to add some document to it. So in the process of adding, that's what we call writing operation. So as soon as you begin to write, the read operation is halted for the other person that you sent to until you finish, you update it, and then the person can have the read access to continue reading the information. So that is what the read replica basically does. And they are obviously this is a computing technologies or system, so they would be advantages and disadvantages. So please, let's try as much as possible to go and then find them. All right, so let's move on to this this very tricky part, which is string pattern match. Please, can you see the screen?
Yes, sir.
Yes, sir. Yes, sir.
Robert, please check your network. All right, so let's talk about string pattern match. And it basically talks about pattern searching, which is one of the important problems in computer science. And when we do a search for a string in our notepad, our Word document file, or browser, or even a database, this is where this pattern search algorithm are used to show the search result that we have. So if you open Word document and you begin to type a word, then this string pattern search algorithm takes place and begins to work to now give you the information that are related to your pattern. So let's take this string for instance. Now text document. Now we are trying to search for this pattern here. So as soon as we try to search for the pattern, we try to get content that are related to what we are searching for. Right, so that is what the string pattern basically does. And for us to be able to understand the string pattern or how the string pattern or pattern search algorithm works, this man over here, not Morris Pratt, wrote about the algorithm where we used to search for patterns in our file or document. And we mostly call it KNP algorithm. So the problem with the basic pattern search is the issue of backtracking. However, the KMP is one of the linear time algorithms that exploit the observation that every item a match or a mismatch happens, the pattern itself contains enough information to dictate where the new examination could begin from. So the backtracking basically means that in the native pattern search algorithm that we have, if you begin to search and you literally then find information or that you have to go back and refer to your previous pattern. However, this KMP algorithm just eliminates that particular portion for us. And we see that it's a linear time algorithm. Now let's look at how this KMP algorithm can be put into effect. So one thing that a KMP algorithm pre-processes with a path, which is a pattern, and construct an auxiliary LPS of size M. Please, I hope you are following. All right. So these are the processes that the LPM algorithm basically goes through. So it processes a part, which is a pattern, and it constructs what we call an auxiliary LPS. And the LPS is longest prefix suffix of size M, which is the same as the size of the pattern that we have. So the M is the same as the size of the pattern that we have. And this LPM is used to skip characters whilst the matching is being done. So now let's look at how to construct the longest prefix suffix. And I believe all of us know prefix and suffix. Please, if you don't know suffix and prefix. All right. So let's take this particular pattern, for instance. AB, BAA, CAA, BAA. We are not going to construct all of this. This is the LPS for this one we have. And please, we are not going to do for all of them. I think when we get to either here or the second one, we stop, and then you might want to go and continue from there. And in this process, we do it character by character. We construct the LPS character by character. So when we start from, we take the first character, which is A, right? And then that is the substring we are trying to see if it matches our pattern. So A, there's nothing for us to be compared with. That is the suffix and the suffix. It is only this is only the suffix that we have. We don't have a prefix. So this is the prefix that we have. We don't have the suffix to compare to see if we have the longest from it or not to get the LPS. So obviously, almost always the first character has the LPS of 0. Please, are we clear? All right. And now move on to the second character, which is A. So AA, the longest suffix and prefix of AA is what? Let me see if I can draw on the screen for us to see. So let me use S. So this S is the suffix, right? So we have this one is the suffix A. So the LPS, as I said earlier, is going to be 0. 0 over here. Now the next character you're going to look at is AA. Please, I hope you are following. So now, so the prefix and the suffix, we have this as a prefix and this as a suffix. So that means that A is equal to A. And the LPS, which is the longest prefix suffix here, is 1. Please, are we following? So we have 1 as the LPS. Now we move on to the next character, which is A. Please, I want you to help us. What will be the next character?
AAB.
AAB.
All right, so AAB. So which one is the, now let's compare the suffix and then the prefix. Mind you, this is the suffix and this is the prefix. So AA is the suffix and AB is the prefix. But then there's no match in them. So that means that this is going to be 0. It's more like AA is not equal to AB. So this becomes 0. Is that what we are following? Now, similarly, we can do for the next substring. We can do for the next substring. Who can help us get the next substring?
AA.
AA.
BA.
AABA. Okay, so we have A, B, A. So do we have, this is B, sorry. So we have AA and then BA. But then we have this as suffix and this one also as suffix. And then AA and AB are not the same. Please, are we following?
Sir, please, no, I'm not getting the whole thing.
Yes, I'm confused like why. You can go back a little.
Hello, sir.
Um,
Yeah, we are totally confused. So.
yeah, just a minute. So what I'm saying is that we are trying to build what we call the LPS so that we can use that in our KMP algorithm. So in the KMP algorithm, what it does is that it computes the LPS. Maybe your hand is up.
Yeah, sir, please, is it possible that you give us per the diagram you are creating or the matching, can we have a new blank space so you can do it? It should be so that it will be clearer for some of it. If it is possible, please. Thank you.
All right, let me see if we can. Please, just a minute. I'm not finding any blank sheets.
Hello.
Yeah, hello.
So unless you open Microsoft Word, then we work it out there.
All right, so I think this is fine, right?
Yes, please.
So let's okay. So let's use a different pattern, and then when we are done, you can go and try the other one as well. So let's use this particular one over here. It's a ECA. So this is the pattern we have, and to make it quite easy for us, you might want to construct a table so that we keep all the substring and the others, the LPS and the others in it to make it a lot more easier. So let's create a table from here. Obviously different colors. So this is from so this is this. So the first one contains the substring. And this one, please you can tell us the substring that we have. The first character, sorry. And that one can also be the substring as well. So from A, B, C, A, what is the first character we have?
A.
Please, we are doing it together so that when I finish, you won't say over again. Okay, so we have A over here. Right. So what we do is that, let me, this is S and this is N. So the S here is start and this is N, E. Now let's look at the longest match because we say that longest prefix suffix. So let's see the longest match within the start and the end. So you can use something like L, M as the longest match. And then finally we get the LPS as the longest prefix suffix. So we have A as a substring. So what will be the starting and the ending for this particular character here? Anybody? The starting and the ending for this character?
Yeah, please, I think it's 1 and 0.
One and 0. Where's the 1? Where's the 0? There's actually nothing over here to compare because you don't have an end.
Okay.
And as I said earlier, mostly the first character has LPS of 0, so this is going to be 0. Now move to the next character. So the next character, as part of the next character, we have the first character as well. So it's going to be A. So this is the previous character, and this is the next character, A. It starts and the end. So we have A to be equal to A. That is, the start is A, which is the same as A. And the longest match is A. So it's going to be 1. Please, are we clear? Now, what will be the next substring or next character?
A, B.
So A, and then B. Now we have the starting and the end. So the starting is AA and the end is AB. Please, are we clear? The starting is AA and the end is AB, which basically means that there's no match over here. So this two, there's no match. So we can put a dash over here and then the LPS is going to be 0. Is that clear? Now the next one. Now the next one is AABC, right?
Yes, sir.
So I just hope AABC can enter here. So A, then we have B, and then C. Do we have a match start and end?
No, please.
Do you have a match start and end?
No, no, please.
Okay, so that is going to be 0 as well. So 0, 1, 0, 0. So these are the LPS that we are building. 0, 1, 0, 0. Now we move on to the next. This is how we are clear with this one. I'm clearing it off.
Yes, please.
All right. Hello. Please, the person who is not muted, can you mute yourself? All right, so now what's the next longest surface prefix? I mean the character. Which one are we now? We've done this. So we are at this place, AABCA, right? So the end and the start and the end, do we have a match?
Yes, please. A as a start and A as an end. 1A.
Yes, obviously. So we have A.
It's two. We have A at the start and A at the end, and another A, the second A, and then the last A.
Yes,
We've
but
not
then that's
gotten to the last A.
yes, but we are still at this place, please. We are here. So the start is A and the end is A. So we have a match over here. So whenever you see a match between the suffix and the prefix, that becomes 1. So this particular one gives us 1 as the LPS. I hope it's clear. Now moving on, we are now considering all of the string, which is AABCAA. Do we have a match at the start and end? So we have AA, and we have AA. So whenever you have a match preceding another match, you add 1 to it. So this is going to be 1 ideally. But since we had earlier a 1 over here, it means it's going to be 1 plus 1, which is going to make the LPS 2. Please, do we get it?
So it means throughout we've gotten 2 1s. So we are going to sum them up. Is that what that means?
They should follow each other, not throughout, but let me list all
the previous one we just had 1 match. That is the first A is, and the others we didn't have much, so we had zeros. And getting to the last ones, we have 2 A's here, 2 A's below behind, and we are having another 1. So it means that throughout we've gotten 2.
Yeah, but that is not why we are getting the LPS to be 2 for the AABCAA. That is not the reason. So let me list all the LPS we have. So we have 0, we have 1, we have 0, 0, then 1 and 2. So this place means that there was no match in our search during the first character. However, in the second one we had a match, which was AA. But in the subsequent one we had a no match as well, and the other one we had a no match. But moving on to the AABCA, we had a match, so we marked it as 1. Moving on to the last, which is AABCAA, we had a match. Because the matches are following each other, that means we increase the latest LPS to 1. I mean to 2. So assuming that moving on, we added another A here. And then after realize that we had another AA as a match, then it means that these two have to increase to 3. If we have a mismatch, then it's going to be 0. Then we start all over again. Did you get the concept?
So, please, if I understand, is it because we had AA at the start and AA at the end? Because they were 2 straight away, then we are making the side 2.
Yeah, in this example, you may say that, but then probably in some examples, it wouldn't be like this.
Okay.
That is why I want you to understand that whenever you get 2 consecutive matches or more than 2 consecutive matches, then you have to add 1 to the previous consecutive match to get the current LPS. So assuming that we had, let me use the color, we had 1 for one of them, and then subsequent we have another match that is going to be 2. Then the next we have another match that is going to be 3. Then the next we had a mismatch, then it's going to be 0. Please, are we
And
clear?
so, what if we have another one again? Then we have to start the one all over. We want to be saying
Yes,
4.
exactly. You start from 1 all over. You
Okay.
don't start from 4, you start from 1 all over in that order. That is why if you look at the slide, we have 5 over here. It means that from 4 here, from this place going, we had a match from here up to the last one here. So from this one I've circled, there was a match. It preceding one, there was a match. So we increased this by 1 to get 2. The next one was a match. We increased this by 1 to get 3. The next one, there was a match. We increased it by 1 to get 4. The other one, there was a match. We increased this by 1 to get 5. Please, do we get it?
Yeah, sure. Yes, sir.
Yes, sir.
Actually, not, sir. Small.
So, if there was a mismatch just behind the 5, then everything becomes 0. Is that what that means?
Not everything as in, can you clarify what do you mean by everything? Like the whole of this?
What I mean is that probably if there was a mismatch just behind, there was another, let's say C.
Okay.
Yes. Then it means after the 5, you have 0.
Exactly. And then we start counting again.
Maybe.
Yes, sir.
I think with the example you gave, if you bring C, then the match is going to be 6. So because if you look at it, we have A, B, A, C. And then
But I think we are comparing from the start. Is that not it?
So for example, if you should have something like a D, if you should have something like a D rather after the 5, it means that we are going to have a mismatch then it will go to 0. And if any other match comes in, then it will start from 1 on and keep adding up whenever there is a continuous matching. Thank you.
Yes, sir, I get you. But if there is a C, which one are we comparing the C to? Would we compare it to the C in the middle, or we are starting from the preface? That is the first what do you call it?
When you start from the beginning, right? You are going to have A, B, A, C. And then and if you look at after the C, you're going to have another A, B.
Okay. I see the repetition over there.
Yes. So that will be a match. That will be a match.
All right.
Thank you so much.
I'm really happy that you understand this clearly, because I took some students who was a help for me. All right, so that is how we compute the LPS for the KMP algorithm, and these are some samples that we can get as well, right? So with this, now the computer will have to now compute the match in the values using the LPS instead of going back and forth. As soon as it get to 5, just a minute. So as soon as it gets to 1, it will realize that there was a match somewhere. So instead of going back again to start from the beginning, it will just start from this place and then move on with the search. The same way, if it got to 5, instead of going back to 0, here to start, it will just start from the 5 because there's a match over there, and then there's no need to go back and start all over the search again. Please, are we getting it? Jackson.
Please, I wanted to ask my colleagues that am I the only person who is confused, because it seems I'm not getting the whole idea. So if someone is together with me, please raise your hands, because I'm completely at sea.
Jackson, I'm with you.
I'm also not getting it. So
Jack, I'm also
I'm not
totally
getting
confused. Everybody is confused here.
Wait,
my problem is that
you are totally confused. We are all confused.
Sir, the confusion is coming from your illustration.
Some of us, we are completely.
I think that if you are to open Microsoft Word and you are to do the, since you were, using that freehand sketch, the whole thing I was confused. I can't even differentiate between A and then F. So if you could open Microsoft Word or any other application, that the A will be A and then the 0 will be 0. So we'll be very grateful, because some of us are slow learners. Thank you.
I see. Okay. Let me try my best. Can you see the Word document?
Yes, we can see.
Yes, sir.
No, sir. I can't see.
Boss might see something.
Relax, you will see.
Can we see it here?
Yeah, I can see.
I said, please, some of us are new to this, bro. Some of us are new to this. So if you can teach us how to, compare the matches and that.
AB, you are not new. AB, you are not new. We are new.
It's okay. Please, let's focus here. Let's focus here. Let's focus. So let me draw a table for us to see it clearly. And please don't expect to actually get a concept right away. Right? Don't expect to get a concept right away. Because you have to sit down, probably get the videos before you can actually understand clearly. All right, so our headings are going to be mostly we start from the index. I just skipped that because some of you asking me different questions. So this is the index of the string that we have. So this one, for instance, more like a list. So we start from 0, 1, 2, 3 in that order, right? And this is going to be the substring, right? And this will be the start end. Start versus end. And this will be the longest match. Now, ultimately, it will be our LPS, right? Please, are we following? So
Yes.
the index are going to be 0, 1, 2, 3, 4, and probably I think 5. Let me see. This is A, B, C, 0, 1, 2, 3, 4, 5. Yeah. And now we are starting with a character, right? Or a substring. And the first substring we have here is A. Let me do this. So this is the substring we are considering.
Sir, how do you choose your index?
The index start from 0. So here, 0, 1, 2, 3, 4, 5.
Okay. Using the character.
Yes, so this character A is index 0. This is index 1. This is 2, this is 3, this is 4, this is 5.
Okay.
Right. So now the start and the end. So for this substring from here, where is the start? Where is the end? There is a start which is this, but then there's no end.
There's no end. Okay.
So we cannot compare. So no comparison or something. So let me just say no C. That's no comparison. So which one is the longest match? There's no longest match over here. So you can represent it with a dash. And now we come to the LPS. As I said earlier, to make things easy for you, the first character is always the first substring. And that one has LPS of 0. That is clear, right?
Yes, sir.
Okay. Now moving on to the next index, which is this one here.
Okay.
But then it's supposed to be a substring, so we have to add this one to it. So we have, this is our next. So we have A, and then A. Are we clear? Now,
yes, sir.
Where is the start? Where is the end? That is what we are doing the comparison. So the start is A is actually equal to A.
Okay.
Is that clear?
Yes, sir.
And the longest match is A. So that will be LPS of 1. Wherever there is a match, it has an LPS of 1. Okay. So now let's move on to the next one, which is this one here. This is the substring here. But the next character is B, but the substring is AAB. Is that clear?
Yes,
so
sir.
basically the end is AA. I mean, sorry, the start is AA, then the end is this. Are we clear? And then there is no match in this sense. So I can say NM. And then we can represent here as a dash. And obviously, if there is no match, LPS is 0. Now we move on to this one as well.
Sir. Hello, sir. Hold on.
Hello.
Yeah. So we are saying that the start of the one we just did, the AAB, it has no match. I don't get it. Why, sir?
Yeah, so we are comparing the substring. Substring. This is the substring and then the prefix. So it's more like suffix, prefix. So the suffix for this particular substring is this, AA.
Okay.
And the prefix is AB. Do we have a match? AA is not equal to AB, so there's no match as such.
Okay. Okay.
Please, are we clear?
Yes.
All right, and then we have ABC over here. So do we have a match in this? Someone should just tell me.
No.
No match.
There is no match. And then you can represent here as a dash, and the LPS is 0 since there's no match. Now we have this one here. So we have AA, BCA. Do you have a match in it?
Yes. Yes.
Which is the match? Can you tell me?
So the match will be
And the A.
All right,
The starting A and then the ending A.
So A is equal to A. All right, and then we have the A as the match. So since there is a match, then the LPS counts to 1. I hope it's clear up to this point.
Yes, please.
Yes.
Now we have the final pattern, which is this one here. Which is AABCAA. Do we have a match in this?
Yes, please.
So this is AA and this is AA. If you take AAB, there's nothing like AAB here. If you take AABC, it doesn't match with this, but then AA and AA matches here. So we have this as AA equals AA. So we have the match, or the longest match is AA. Right. Very clear. And then as I was saying, if there's a match seeding another match, then we increase this by 1, and then we have 2. So this is the for this particular sample given to us. Please, are we clear?
Yes, sir.
Yes, sir. Somebody to help us understand. So I'm adding another value here, another character here. Someone should help us understand how to get the LPS. This is A. Okay, so this is A, the last one. Who can help us with the 6? 6. This is the substring. Somebody should help us understand it from here.
So in that one, the start string and then the end string, which matches is AA. A matches to AA.
A matches to AA.
Yes.
Okay.
AA matches to AA.
So obviously we have another match here. So we have
another match there.
AA is equal to AA, and then this. So AA. So obviously we have 3.
3, yes. So what about adding B to the list you have?
Okay, so let's add B. Someone should help us get the LPS for this substring. Anybody?
Then please open it up for us. The 7th index will be AAB. AABC. So in this case, we are going to have two matches. We are going to have 1 match, which is AAB. AAB.
Okay. Yeah. So this and then this.
Yes, yes,
right?
sir.
So AAB
Equals A
AAB, and then the match is
AAB.
AAB, and then we have the LPS to increase to 4.
Sure.
Right. However, if that is not the case, that is, we didn't get a match from here, then we are starting from 0 all over.
Yeah, 0.
Okay. Please add B again to it so that we look at that one.
Please,
Yeah,
we have a very long one on the slide, so you can go and look at that one, please.
All
right.
All right.
And if you are finding any difficulties, when we meet next week, we can continue from there. Right. So these are, I mean, this is how it is being calculated. So you can just go and look at it and then see how it works. And we have left some here for you to just complete at your free times. I hope we are clear. All right.
Yes, sir.
Yes, sir.
And this is also an example as well. Consider the string this, and this is the pattern. So trace using the KMP algorithm. We start from base row to 0 and compare string I to part. Basically, that's what we just did, right? So we compare the previous, which is a suffix, to the prefix. If there is a match, then the LPS is marked as 1. If there's no match, the LPS is marked as 0. Basically, that is all. All right, so we have another one, which is, I think, the last one here, which is data compression. I believe all of us are very familiar with data compression, right? In order to help us understand data compression and what it is. The righteous, Johannes, tell us something. Hey, tell us something, just lower the hand. Anyways, data compression is, okay, Clifford.
So, data compression is the reduction of the size of a file while maintaining its contents for faster transmission, and then reducing the amount of space it occupies on a storage location.
Right, that's very true. So, I mean, I don't need to explain further. So that is how data compression is all about. We have two main examples, which is the lossless data compression, and then we have the loosey data compression. Just go and find the differences between them. So some of the most simple and efficient algorithms that can be used for data compression with the Huffman encoding.
Sir, please come again with the types. The one you say you should go and look for.
Lossless and loosey.
Lossless.
Yeah. So we have a Huffman encoding, which, and also have the ASCII code, the fixed coding, and then the Huffman encoding. So these are some examples of very simple and efficient data compression algorithms. So let's look into them, what they are, how you can actually use them. So let's consider the Huffman encoding, for instance. We have this message here, BCC, ADD, up to this CC, and we are asked to reduce the size using the Huffman encoding. So what we have to do is use the ASCII code, which has 8 bits. We multiply that by the characters that we are given, and then we are having this particular 160 bits. Let me take it again. This is a message that's been given to us, and if you count the number of characters or alphabet in here, they are 20. So for the Huffman encoding, we use the standard bit representation of each character, then we multiply that by the number of characters that we have in the message that we are given. which is what we call the ASCII code size, and the standard bit size is 8 bits for every character that we have in the computer system. And the number of characters we have in the message are also 20. So 8 times 20 is going to give us 160. Please, someone should confirm for us if it's 160 bits.
Yes, it's 160.
All right, so for the ASCII code size, the amount of space we need to store this message is 160 bits, right? And then also with a fixed coding size, that is going to be 20 times 3. And the 3 here means that we are representing each of the character by 3 bits. That is what we have over here. So 20 times 3 is going to give us 160. And now with the fixed coding, we have what we call the table size, where you construct a table more of like this, right? And the table contains the special character, the unique characters in the text. Please note, the table contains unique characters in the text. So if you look at the message over here, for instance, BCC, AB, BD, DA, ECC, up to DCC, the unique characters are only 5. So you multiply 5 by the standard bit size, which is 8. This is going to give us 40 bits. Now we also have to calculate the code size, which is the unique characters times this, which is the 3-bit we represented our data with here. And then we are going to get 15. So with the fixed coding size, to get the total size we need to store, we add this plus this plus this. What are we getting? Anybody to help us? 60 plus 40 plus 15.
115.
115.
All right. 115. So realize that using the fixed coding size, the file size has reduced by 45 bits, right? As against the normal ASCII code. That means that we can still move further and then reduce the size using the Huffman encoding. Mind you, this is for ASCII code, and this is for the fixed coding we spoke about earlier. But then we can equally use the Huffman encoding to further reduce the size from the 115 to a more smaller size. Please do understand how to calculate the ASCII code size and the fixed coding size for the message or any information given to us.
Please go over one more time, please.
All right, so for the ASCII coding, we use a standard 8 bits per character. We multiply it by the number of characters that we have. So each of the characters here are represented by 8 bits. So B is 8 bits, C is 8 bits, and then the other C is 8 bits up to the last character. So to get the number of size for the message given to us, it is one of the size, which is 8 times the 20 characters we have. So 8 times 20 is going to give us 160. So we need 160 bits to store this particular message over here, which is not quite efficient. So we move further and try using the fixed coding size to see if we can reduce the size further. And this is what we did. We represented each of the characters with a 3-bit instead of the 8-bit standard. This is what we have here. So right after that, we multiply each of them, which is 20 of them, by the 3 bits represented them with here. So 20 times 3 is going to give us 60 bits. But then with a fixed coding side, we need to store what we call a table. We need to construct a table, right? And for us to construct a table, this is also the size of the table that we need. So the standard 8-bit character times the unique characters we have in the message, which is this message here. So if you want the unique characters in this message, you are going to get 5 of them. So 8 times 5 is going to give us 40 bits.
Sir,
Which means that we
please,
need,
how do you get the unique characters? How do you calculate that one?
that is frequencies. Therefore, your hand is up. Please, I'm coming in.
So I think with the unique characters, maybe in the message you have, let's say, a particular alphabet repeating, let's say, 5 times.
Yeah.
So that one you just count that alphabet once.
Exactly.
You don't count it the 5 times. Unlike
Okay.
the first one that you are multiplying by the 3.
Okay.
Exactly. Exactly.
Okay.
Exactly. So we basically take the frequencies of any of these ones, their occurrences. So if this one occurred twice, you have to record only one of them.
Okay.
So those are the frequencies that I'm talking about here.
They are
Getting the
A, B,
frequencies.
C, E. So up to 5. A, B, C, D, E. 5.
Yes. So if we had a Y here, then it means that the unique are going to increase to 6 rather, because Y is not here. Exactly.
Yeah.
So multiply that by 8 times 5, which is 40. So we need 40 bits to store this particular table we just constructed. Right? And then also to get a code, we multiply the 3 bits represented with each of the unique characters by the unique character, the count of the unique characters, which is 5. So 3 times 5 is going to give us 15 bits. Now when we add this and this, we are getting a reduced size compared to this, which is 115 as opposed to 160 bits. So in a sense, we could say that when we use a fixed coding size, the file size reduced from 160 to 115, which is we have saved 45 bits space in our memory. All right. But then we can do better with the Huffman encoding. Although the file size has reduced using the fixed coding, we can do better with the Huffman encoding, right?
Okay, so sir.
Okay.
Yeah, but I think on the table when you multiply the A by 3, you are getting 0, 0, 0. Can you please throw a bit light on that one?
You mean here?
Yes, on the table. Yes. You see, when you do the multiplication, as you are saying, you are getting 0, 0, 0, 0, 1.
Yes, Clifford.
You know, that one is in the machine language, which is 0 and 1s, binary language.
Exactly. So please just forget about it. I'm just using these ones to see that each of these characters are represented with 3 bits.
Okay.
That's what we have here. Yeah.
Okay.
All right. So as I was saying, we can do better with the Huffman encoding.
Okay.
So please, this is an example for you to go and do, right? And then I'll talk. Please, are you asking a question? All right, so let's talk about the Huffman encoding. Hello.
Yeah, please. I just want to know the 3-bit. How do you come by the 3-bit, or is the machine that gives when you compress?
All right, give me some few minutes. I'll be back.
Yeah. Clifford, I was experiencing some network challenges. So how that 5 they came by that 5, I didn't get it. I only saw that they had 20 by 3 and others. Can someone explain it?
When you look at the message, Richard, you see that the message contains alphabet. And when you look at the alphabet, we have 5 different alphabets in the message. We have A, B, C, D, E.
Okay.
So with the first one, which is the one that we are using, that fixed 3 bits, that one you just, if a particular alphabet repeats several times, you still count it differently.
You count
and
it as one.
multiply by the total number of alphabets, the 3. So that's where we had the 20 by 3. Now the second one, you
So
you count
the tray is about what?
a fixed. It's a fixed
Okay,
code.
it's a constant. Okay.
Yes. But where we had the 5, now when you look at the message, we have 5 different alphabets. So if a particular alphabet repeats maybe 10 times, you don't count it 10 times, you count it only once.
Okay, but just that
So
with
the
the count,
total
we
number
need
of
to represent.
different alphabets. Hello?
Yeah, I'm getting it.
So that is how we got the 5.
Okay, and from the table we are
The
having
base
8
is
times
also
5.
constant. It's fixed.
Pardon? Hello?
I was
Okay.
adding up the 8 is also fixed.
Yes. The
Yes, the 8
8
is the standard size or a standard bit. So the first
And when
one
it
is a
comes to
fixed.
yeah, the 8 and the 3, they
Yes,
are
the
fixed.
3
They
is
are
the
not
fixed
four.
code.
Oh,
That
yeah.
is maybe whatever platform is rendering a compression service. So maybe they can decide to use a 3 for the fixed code. But the 8 is the standard size of a bit.
Yeah.
Right.
All
They
right.
can decide or is something fixed that I don't know. Because
Please,
if you
Solomon,
get
what's
that,
your question? Solomon, can you ask the question
I
again?
was asking of the 3 bit.
Yeah.
That is it generated by the machine itself or you are going to I don't know. Whether when you
Yeah, so
compress it, that's what comes.
you choose to represent the file which way. Notice that when you choose a 3-bit, it's going to reduce the file size. So it's a choice between you, the programmer.
Oh, okay.
Yes. So most of the file compression algorithm, they have something similar to this. But notice that these are the basic ones that we have. The basic file compression algorithm, the fixed size coding. But then the Huffman encoding does a lot more by compressing the file much more than the others that we have. Right. So these 3 bits is a choice from the programmer as to how much you want to reduce the file size. Clifford.
Sir, someone asked how the binary, we got the 000. And I wanted to come in with that one.
Oh, okay.
We have the ASCII table, which has the alphabets with numbers representing them. So, for instance, C is represented by, I think, 67. So, if you want to get the binary code for C, you have to know the ASCII number for that, the alphabet, and then convert that number to a binary, so base 2. And that is where you now get the binary code for that particular alphabet.
Yeah. All right. Thank you so much, Clifford. So now let's move on to the Huffman encoding. How we can use the Huffman encoding to further reduce the file size. And this one has 2 steps. The first thing we have to do is to construct a frequency table, more like what we have over here. And now when we are done with this, we now build what we call a Huffman tree. I hope we are following. So we first have to create a frequency table where you have the character and the account. So in the Huffman encode, we are not going to consider this one. We are only going to consider these particular ones here, the first 2 rows, the character and the count. So let's assume that our frequency table is built from here. Now we have to draw a tree. And we start building the tree from the roots and then up, no, from the leaves up to the roots. So let me see if I can use it here. No, let me use the where they came. so that you can understand it clearly. Let me list the frequencies. Please, I'm doing it once and for all. If you don't follow and we are done, unless someone else teach you. So we have the character. And then we have the frequency. And as I said, the frequency is from a given message. And in our message, we had 5 characters. We have A, we have A, we have B, we have C, we have D, and then we have D as well. And then we have E as well. So the frequencies, A occurs 3 times in the document. B also occurs 5 times. And then also C occurs 6 times. D occurs 4, and then E occurs twice. So this is the frequency table that we have built, right? Now we are supposed to build a Huffman tree. And for us to do that, okay. And for us to do that, please, sorry, I'm coming, and let me see if I can use a different tool to draw the table for us to see it clearly. Please take note of the frequencies. If I'm making a mistake, I can just draw my attention so that we can. All right, so this is what we have. So to draw the tree, what we have to do is start from the leaves and then build upon it to the roots. So let me pick this one over here. And then we mostly select the list and frequencies. So please, you can help us from the graph, from the frequency table, which of them is least. So we select the 2 least frequencies, we join them together in that particular process. Yeah, so who can help us?
E and A.
E and A.
So we have E over here. So E. So we have E, and then and then let me see A, and then E. So we have to now connect all of them together to form a different another node. So we connect this. No, so but notice that what is their sum? So in their sum you're going to write here.
Sum is 5.
So the sum is 5. Okay. So now we have E and A, the sum is 5. Now we have 5 over here. Which of them is the least? So we connect it to the 5. So we have 5 and 4, right?
Yes.
Okay, so and then 4 is also D, so you have this one in there. You have D. So what will be the sum? 5 and 4 is 9, right? Then what's the last one?
Say C and the 6.
C and 6.
Mommy. Sorry. Mommy. Say the next one is B. B rather 5.
B.
Yes, sir. Before the C.
Okay, so B is also 5. So we connect B to here as well. So we have this. All right, so this 5 and 9, right? That's going to be 14. And finally, we have B. So it's going to be B, we change the direction small.
So no, the final one will be C.
Yes, it will be C. I'm just trying to reconnect so that we can join them properly. All right, and then we have C over here, which is supposed to also connect. Here. Please, the diagram is not drawn to scale, right? So then it will be 20. All right, so this is what we have for the Huffman tree. Did you understand how it's being built? Yeah. So what we have done now, we have to get a code for each of the values here so that we can represent them in binary digits. And those codes to the left happens to be written, we take them as binary 1, and those edges to the right, those to the left are binary 0, and those to the right are basically 1. So this is going to be 1. This will also be 1. This will be 1. This is 0, right? This is 1. This is 0. This is 1. This is 0. This is 0. Is that clear? So those edges to the
Derry.
madam.
Yeah, I think some hands are up. So if you can call them,
Okay.
someone's hand is up.
The righteous. I've been calling you. You're not minding me. The righteous. Michael.
If they are not responding, let's continue. Okay.
Okay. All right. So madam is around. She will address you very soon. All right. So as I was saying, when we build a Huffman tree like this, those edges to the left are represented as 0 bits, just as you've seen, and those to the right are represented as 1. When we are done, we now have to trace from the root to each of the various special characters that we have, so they can write their binary representation, then get to know the number of bits that they can store, or they will be stored in the computer memory or system. So for this character B, who can help us read its binary representation from the Huffman tree? Anybody? We are tracing from 20 to B. Everybody is quiet. Okay, so it's going to be 0, 0. And then for D.
Hello, sir.
Festus.
So, my concern is about the arrangement. First of all, you let us understand that you take the least characters, that is E and A. Now,
those with the least frequency.
Okay, so from that time onwards, all the other least ones were being arranged at the left side of the E and A, but with the C, it came at the right side. And since we are to assign numbers to them, that is to assign zeros and ones to them, based on where they are, whether being at the right or the left. Now, what will be the arrangement of the characters if you are to go by the right arrangement? Because I don't know the procedure that led to the C going at the right hand side, whilst the others that preceded the E and the A were on the left hand side. Thank you.
All right, please, another question.
Hello, sir.
Hello.
Yeah, that was the question I wanted to ask.
And I've been calling you, not minding me.
No, sir, it was the network.
Network platform.
Okay, so yeah, so but then the idea is that you know how to draw the tree.
Yes, please. From the beginning, I was there from E and A.
You were following. All right, so let's get the binary representations first, and then I'll address that particular question. Right. So for D, we have 0, 1, 0 to represent the binary. Mavis.
Yes, sir. Please, I still think that C should come in front of the B from the left, because that. Why is it that the C is? I thought we were struggling for space. That's why you brought the C there. Other than that, the number assigned to the C there should also be 0, because it's also at the left. It should be at the left side. Then I can understand where we are going.
Okay.
Are we
okay,
changing
so,
the C to the side, or it should be there then, so that probably we can follow you? Thank you, sir.
So let me change it then, right? So you realize how messy the thing is.
Who is that?
Massa, behave and behave.
Righteous, be careful. Righteous.
Boss man.
Hello, please, I said doc is here. I mean, I know at least. All right, so this is what we have. This is 0. This is going to be 1. This will be 0. This is 1. This is 0. This is 1. Okay, so I think this drawing is a little bit closer to scale. All right. So this is what we have. So for C, we have it to be C is equal to 0, right? And then B is going to be 1, 0, 1. Sorry, 1, 0. And then D, which is this, would be 1, 1, 0. Right,
Hello,
someone to help us continue. Hello.
Listen, this is Christian.
Okay.
With what we're doing now, some of us will look at the practical aspect. I was very grateful. Practical aspect. I'll be very grateful if you are teaching us or you walk us through how to do it practically. As maybe we all have our machine, do this, we do this, we do this. Rather than maybe we just watching you. Maybe after that, we forget. So if we are doing practically, we all open our machines, do this, then you do this. I think it will stick in our mind rather than we watching you. I think some people are not even online self. So when we are doing practically, it will help us. Thank you very much.
Where practicals means,
like with what you are doing now, because
yes, I want.
Because he is demonstrating, so like, which I don't get. He's demonstrating, so if you have a question, you might ask, but I don't see how practical this stuff to be done. He's demonstrating to us, so if there's any question, probably to me, you can ask instead of going by that route.
All right.
So the practicals cannot be possible because I won't be able to see everybody's screen and try to direct them what to do. So just look at the demonstration and then we move on. Right.
So I think he's talking about how do we apply this on our application, the
No. We have the Huffman encoding already that you can use to compress the files. What is the algorithm doing? What does it do to compress the file? That's what we are talking about here.
Okay.
So it basically takes the various characters in your text, and then it forms a Huffman tree like this, what we have drawn. And then right after that, the trees, those to the left are represented as 0, those to the right are represented as 1. And then when it is done, it computes the bits to store each of the characters in the computer memory. That is basically all. So for every character in the message that we have earlier, the bit is 10. And also for D is 110. Then for C is 0. Now let's do for E, sorry. Who can help us do for E?
Sir, please, I want to try.
11.
Sir, 1110.
1110. Okay. What of A?
1111. So 4 ones.
4 ones, yeah.
Okay, so this is how the file is going to be represented in the memory space. But you realize that some of them are in 4 bits, others are in 2 bits and 3. So it's better to make it balanced by adding extra bits to each of them to make sure all of them have the same number of bits. So assuming that this A had 5 bits, and you have to make sure all the others have 5 bits. And to do that, you add the bits. Is it after or before? So the bits should be added over here.
Before. That's separate.
At the back, from the back here, to make them 4. And do the same over here as well. 1. And then you do for the C also. 1, 2, 3. Please, I hope we are clear.
Yes, where do we get the figures from? The bits, the 111, the 001, and where did we get?
Please, can you go and watch the video? Code will give it to you. Right.
Sorry, please, I have a question.
All right, Davis.
So please, my question is, you said the Huffman tree, the figures to the left are represented by 0, and the ones to the right are represented by 1. But the left of what and the right of what? That's where I'm confused, please.
We all have left and right. So for me, this side is my left here. This particular line here. This line I've highlighted is my left. This is right. This is left. This is right. So let me make it simple for you. To the left and right of each node, this 20 is a node, and to the left of it is this one here. To the right is this.
Okay.
Yeah. Please, the person who asks, how did we get the 0010, 011, and the rest? Please, I beg you in the name of God. Go and get code videos and watch it. You get to understand where we had this. We didn't do any magic. Please, any question? Please, any question?
So
all right.
With E, I see something wrong with E. The 1110. E.
Oh, how? What is wrong with it?
Because I see 0110 rather.
No. We start from the top, not the bottom.
Okay.
Yeah.
Okay. Thank you.
All right. So basically, if we have the text like this, B, C, C, A, B, E, B, D. So wherever you see B, you put this character there, this 001 over there. So this is going to represent a B in here. So we have this representing B in our case. Now C is going to be 1, 2, 3, 4. And then C 1, 2, 3, 4, B 0, 0, 1, 0. Then another B 0, 0, 1, 0. Then we have D, which is 0, 1, 1, 0. So this is how you can represent the characters. And for you to be able to get the bits correct, you count the number of bits 1, 2, 3, 4, 5, 6, and then you represent that as the storage size for the message. So this particular message, for instance, you can count the number of bits here and then represent it as this. Please, are we clear?
Yes, sir.
Is there any other question before we leave here? All right, so I think Doc is around. She'll address you very soon. Hello, Doc.
Hello, sir.
Hello, Christian.
Yes, sir. Please, with respect, a brother asks a question. I'll be very much grateful. You know, that is why you are teaching us.
Yeah.
So that you can please highlight more for him. Maybe watching the videos he might not understand. So if
All the question about.
he asked that where do you get some ones or some 0, 0 something, and that was when he said you should go in. Maybe somebody can help him. Maybe like you should give you the follow so that somebody will help him. Thank you.
I suggest we are using time and looking at the question that he asked. I mean, it's just to pull us back. Even he was only demonstrating that someone even recently asked a question that he thinks it will be 0, the E will be 0, 1, 1, and he demonstrated that no, it will not be 0, 1, 1, it will be 1, 1, 1, 0. So he could have taken a clip to know where we are coming from with those zeros and ones.
All right.
Other than that, you get in, and we
Apart
are
from
also
that,
preparing.
the way the question was asked was not in the right way. Maybe due to network or something. Could you please go back a bit? You can't just go straight and say where from the 1111. No, that's not polite to me.
All right, please let's close from here. Hello, Doc.
Hello, Derry.
Hello, Doc.
Yeah.
Please, I think we are closed for today. Any words for them?
All right. Good morning to you all and welcome to algorithm class. Yes, so basically this is the fundamental to most of the computing programs as in computing courses. So if you can write a good program, if you can do a good architecture, if you can do good networking, the fundamentals is algorithm. So I would entreat all of you to pay much attention as we take you through this course. And also, this is an online class. So usually that's why we are recording the video. So usually we would encourage you to do well, to listen to the video, to watch the video again. And then after watching the video, if you don't get the understanding of the video, you can write down your points or you can write down your questions. And then in the subsequent week, when we meet for class, we will take questions and then you can bring your question up for us to address.
Okay, madam.
Okay, so we will encourage you to watch the video over and over again because this is more of computation, this is more of math. And so, doing math online is quite not that easy. Not all of you might be able to follow, but perhaps if you take it by yourself and sit behind your computer, you should be able to understand some few things. And then you jot down your questions if there are any, and then the following week we can address it for you. Please, is that okay? Yes. And
Yes,
as we'll be
madam.
taking you through the course, we encourage you to accord us the maximum respect as possible. Okay? When you come on the line, kindly mute yourself. You know, this is an online program. We are recording the session. So if you don't mute yourself, it becomes difficult to get a good recording for you. And also, we don't need your videos. So when you come on, put off your video. If you put on the video, we can't get a good recording for you. So do well to put off your video and then you mute yourself. If you have a question, you raise your hand and then we address your question for you. But if you don't mute yourself, if you don't put off your video, the recording that we will get for you will not be of good quality. So kindly do well to adhere to this for us so that we can get you a good recording for you to be able to follow whenever you want to watch it. Please, is that okay? And I will repeat, please do well to accord us the necessary respect. If you ask a question and then you don't get the answer that you require, kindly do well to reiterate your question. The fact that we are teaching you does not mean we understand all questions that you ask. Maybe we might not get the perspective from which you are asking the question. So if an answer comes and it doesn't really answer your question, do well to reiterate your question for us to be able to address it to you. Is that okay? So
Thank you very
if
much.
there are there any questions whatsoever?
Yeah, it's a comment, Doc.
Okay.
I thank you very much. I have a small concern I want to address. Please, I will beg of all of us. We are all matured. We all have families. Some have families, and we are doing this course. In the event that you don't understand anything and you ask, yes, Sir was asking me to go back to the video. I was thinking it could have been more appropriate. Oh, we got this number from this. You know, we are dealing with network as well. Sometimes your network may go off and then come back. So if you don't understand anything and you ask, it is not as if maybe you are not following the lectures. We are all following, but sometimes you may get your link may go off or something. So if you ask something, please, we are also asking that you be polite enough to give us an appropriate answer. Thank you.
Okay, well noted. But I don't think he had any bad intention for saying that. So just for example, maybe we have about 100 people online and 20 people, their network keep misbehaving. So this person come back, ask this question, oh, my line was misbehaving, so I didn't hear this. He will repeat himself. This person will come, the same question, he will repeat himself. This person will come, the same question, he will repeat himself. So I'm sure it's from that perspective, that is why he's saying that if you didn't get anything, it would be best to get the video. Okay, because other than that, people's network will keep misbehaving and he will be repeating himself a particular thing over and over and over. And I don't think anyone does not like repeating themselves. I don't think you would want to repeat yourself for more than 5 times. I don't think so. Not to talk about 20 times. So I'm sure from that perspective, that is why he made reference to the fact that if you can get the video so that the portion at which you got your network distorted, you can listen to that portion, and then if you still don't understand, the following week you can bring out your questions and then we address it for you. I believe that is the perspective from which he said you should reach out and you should get the video and then watch. Is that okay?
To add to that, Richard, I think your question was straightforward. You could have at least just jump in and say, we're from the 00. I think to some extent you should also be polite in asking questions. Just like you said, we are all matured. So in as much as we want each other to be treated Richard, I think going forward, you can know a way of asking a question. We understand we all have network challenges. So going forward, let's know how to ask questions when we have challenges.
Okay, Doc and colleagues, today, in fact, the lectures went very well. But to my side, there are some portions I didn't understand.
So, ladies and gentlemen, let's focus on the understanding part, and then let's leave the blame apportioning that things didn't go down well with, we are all human. Sometimes we make mistakes. So,
Okay,
Rich and
so let me
Robert,
let me come
so
in
let's
here.
focus on
We are
the other
not.
part.
Let me come in here. We are not trying. There are no grievances. We are not trying to solve any grief. Actually, I was supposed to address the class before the lecture starts. I would have made mention of all these things, but I missed the time a little. That is why I had to join later on, and I had to do this commenting at the latter part. Okay, so as I made mention, this is our first class, and of course, this is the first time we are meeting ourselves, so you don't expect things to be 100%. So I'm sure subsequent classes, these things will not come up again. And as I said, if you don't understand anything, please watch the video, and still, if you don't get it, the subsequent class, ask us your question, and then we'll address it to you. Is that okay? At times, the teacher might be teaching, but you might not be following. When you go and sit by your computer, you could see that, so this cheap, easy thing, and I was not following online, you see. So let's try as much as possible to revisit the videos and then watch them again so that we'll get the fundamentals clear, because this is the fundamental. Today's class is fundamental. So as we progress, it will be much more difficult. So do well to watch the video again before you come for the next lecture. And if you're asking a question, know how to put it. Respect is reciprocated. So if you don't respect someone, you don't expect the person to respect you back. So please accord us the maximum respect and maximum cooperation as possible so that we can also reciprocate it to you. We know we are all adults. This is an adult class. So please, let's behave as such so that we'll have a fruitful semester, a fruitful cohort. Please, is that okay?
Doctor, thank you very much. And then we shall definitely meet next week, Doctor. Thank you.
All right.
Please,
So
Doc.
do have
Hello,
a
hello,
pleasant.
please. Please,
Please,
most
Doc.
of the
Please,
first
Doc.
block today,
Please.
the
Please,
recordings.
Doc. Please, Doc. For Wesco and UCC, when it was time, we joined the link, but we waited. The lecturer didn't show up, so we have to opt for this link. When we even join this one, too, we have to also plead with the lecturer to go back and start again. So actually, I don't know whether we have different lecturer for this algorithm or we are supposed to be joining this class.
Please be joining this class. So all the 2 lecturers, we are on this call. Okay? Is that okay?
Yes, please. Yes, please.
Yes, so be joining this.
Doc,
Study,
Doc,
and
Doc,
I
it's not
myself.
okay, Doc.
Come again, yeah.
Doc, the problem is that, UCC and then Wesco and then the other group, anytime we join, the number is too much. So sometimes during questions and answers, it prolongs the whole lesson. So I think that with the first block, we were segregated into 2. We had UCC and Wesco, and then we had, I think, Cape Coast and the other people, so that you would be able to, channel our questions very well. Because sometimes you have questions, but looking at the number of hands that has been raised up,